can see the presentation well?
Yes. No
Yeah,
problem.
all right. Again, good morning, good afternoon, good evening, everyone. Thank you all for the invitation and the nice introduction. So I believe I can skip my self-introduction here. Today I'm going to talk about some assumptions we often use in modeling and design ACC and CACC systems, and the potential risk if we ignore some intrinsic properties of physical systems. So Yu Zhang also contributed to this presentation. So he was a former PhD, he is a former PhD student at Tongji University when he visited me in Delft. And now he's in the autonomous driving group at Meituan in Beijing. All right, without further ado, let's have a look at what are out there in the media. So I hope you all agree with me that our traffic systems today are far more than perfect. The media sometimes portrayed automated vehicles as the solution for solving the traffic problems, both congestion and safety problems. But we also know that these systems are far more than perfect, either for the testing vehicles or the production vehicles. We see the news that they have accidents, either caused by the system itself or the unexpected interaction with other road users. So as a traffic engineer, we are really interested in several fundamental questions, including, well, whether they can handle complex, dynamic, and mixed traffic environment. What are their impact on traffic flow, especially at what conditions and magnitude they can mitigate congestion and safety problems. As the engineer, we also want to go one step further. So how can we guarantee collective traffic benefits at the early design phase of the CAV systems? And to be able to answer these questions, we do need sound assumptions, models, simulations to design and test the performance of CAVs. There are clear differences between automation and human drivers. Here is a non-exhaustive list. So on the left, I list a few properties of automation. On the right side, you see those of humans. So you can argue that automation may give you accurate control of your vehicle. So if you set your speed at 100 kilometers per hour, the automation system can precisely track this speed. And the automation can also be reliable if well designed, and it can react faster if it can communicate with other vehicles or infrastructure. But these are actually not very good aspects for human drivers. So we cannot precisely control our speed or steering. We are prone to impact performance under alcohol or drugs. Our behavior are sometimes irrational, and we adapt our behavior based on the dynamic environment. On the other hand, automation actually, if you rely only on onboard sensors, the perception is actually not very fast. It is a challenge for automation to understand complex driving environment, and it's difficult for them to predict other traffic participants. And the onboard sensors are also occluded therefore you have limited line of sight. But for human drivers, experienced human drivers are very good in understanding and making decisions under complex environments. With the blink of an eye, you wouldn't know whether a pedestrian in front of me will cross in front of me or wait. Okay, and we also often observe and react to multiple vehicles. So these are actually advantages for human drivers. Now we can see that human and automated driving are characterized by complex dynamics. And the question is, are our assumptions, models, simulations capable of capturing these dynamics and differences? In this slide, I list some of the typical assumptions I encountered in literature regarding the ego vehicle, the surrounding vehicle, and the traffic environment. So what we often see is that for the ego vehicle, either automated autonomous vehicle or connected automated vehicle, have these zero delays in the sensors and the communication, have zero delays in vehicle actuation system. The vehicle dynamics is deterministic, and there is no limits on the sensor range, and there's no limits on the operational design domain. And therefore, there's no human automation control authority transition. Now, we all know that all the automated driving systems we are talking about, all are being developed, have limited operational design domain. And this is clearly that we are missing something there. For the surrounding vehicles in mixed traffic, I want to make the pointer. So that for the surrounding vehicles in mixed traffic, we also use simplistic assumptions like their vehicle dynamics. Especially, I want to point out here is the lateral motion. So if you know that in many traffic simulation environment, the lateral motion are lane-based. So when you make lane, so the vehicles are often centered at the lane center. So there's no lane keeping behavior modeled actually. And when you change lane, the vehicles either jump instantaneously from one lane to the other, or jump in a fixed duration of time. So this is also an open loop process in the sense that once you decide to change lane, there's no way to abort the lane change or change the lane change plan. We also use a lot of deterministic human driver behavior models to model human drivers. And when we design CAV systems in mixed traffic, we often assume that human drivers behave according to some microscopic traffic flow models like car following or lane change. And we assume we know actually the structure and the exact parameters of these human driver models. So this is actually a quite strong assumption. For the road environment, we also see a lot when we assessing the traffic flow impact of CAVs. We use single lane homogeneous section without bottleneck. So this is clearly also you miss some traffic flow phenomena that cannot be captured by the single lane environment. In the three literature I posted here, we did some attempts in the last few years, try to relax some of the assumptions I listed here. So we do show that by relaxing the assumption, we identify the differences in the benefits of automated driving system. So we really should be careful about making certain assumptions and the validity range of certain assumptions. But I'm not going to talk about all of them. So today I'm going to focus on the first 2 points, which related to the delays in the sensors, communication, and vehicle actuation systems. So let's start with the ACC system. That is the topic of this webinar series. ACC, in my definition, is an autonomous system in the sense that these systems only rely on onboard sensors and there's no communication involved. So they, in general, operate at cruise control mode at some desired speed when there's no predecessor, and then follow the predecessor with some desired distance, which is often a function of ego vehicle speed. And you also want to track the speed of the predecessor with zero speed difference. Such systems are often myopic in the sense that you only react to the direct predecessor. Because of physical property of the sensors and actuators, there are actually delays in the information you get from the on-board sensors, and there is also time lag or delay in the actuation part of the system. So now let's put them into a bit more formal setting. Let's give some basic formulation of ACC system. So here we consider this green car, an ACC vehicle I, follow an arbitrary leader of vehicle I minus 1. So we formulate this state vector capital X with different signals, including the S is the spacing or the gap between the two vehicles, and the predecessor speed, equal vehicle speed, and equal vehicle acceleration. We want to know the system dynamics. So if you differentiate this state vector, you get relative speed, acceleration of the leader and the equal vehicle, and the derivative of the acceleration of the equal vehicle, which is the jerk, is formulated in this fashion. Here we have this tau I is the actuator time lag, to be precise, and the UI is the control input we want to compute. Okay? And AI is the actual vehicle acceleration. So what this says is that with the tau I, you cannot realize your desired acceleration instantaneously, but this needs to be realized in a lagged time. Okay? And how do we design UI? So there are different ways, right? So in general, when we compute this UI, we formulate it as a function of spacing, equal vehicle speed, and the predecessor speed. Now we want to include delay in there, so these three signals are subject to a delay CACC. And when we put this control law back into the system dynamic equation, you got this closed loop formulation of the system. A typical or a well-known control law is linear constant time gap policy, which I posted here. Is the desired acceleration of vehicle I is proportional to the speed error, so the speed difference between the predecessor and the equal vehicle, and the gap error. So that is the real gap minus the desired gap. And the desired gap is a linear function of vehicle speed, where TD is what we call the desired time gap, and S0 is some minimum distance at standstill conditions. So that's the linear constant time gap control law. Now, with this formulation and with some, we go to the definition of string stability. Well, in general, we can say there are two types. One is very strict, what we call the strict string stability. What this says is that this Hz is, let's say, in general, a disturbance transfer function, and ESI is the disturbance of the vehicle I, and the ESI minus 1 is the disturbance of the predecessor. For strict string stability, we require each leader-follower pair. Yeah, we examine each leader-follower pair. We require that the disturbance of the follower is smaller than the predecessor. And another, a bit more weaker concept is head-to-tail string stability. Is that I don't really care what happened in between the platoon. I only care the first, the vehicle in the platoon, and the tail of the platoon. As long as the disturbance at the tail is smaller than that of the head, then I say this platoon is head-to-tail string stable. Okay, with that definition in mind, let's go to if this is a homogeneous string, so if all the vehicles are the same, then there is no distinction between these two definitions. So let's look at the homogeneous platoon case, and here I repeat this general formulation of the control law. F as a function of spacing, gap, the equal speed, and speed of the predecessor. With some standard Laplace transform technique, you can actually derive the disturbance transfer function between leader-follower pair. Okay, so these I directly put the results here. So this transfer function actually can be expressed by the control law and the system delays. So what you see here is this tau I, again, is the actuator lag we talked about. This CACC is the sensor delay. And this FVP is the partial derivative of the control law with respect to the preceding vehicle speed. And Fs is the partial derivative of the control law with respect to the spacing. And this Fv is the partial derivative of the control law with respect to the equal vehicle speed. And omega is the angular frequency of the disturbance. So with these, we can use these to apply to different gap policies, desired time gap policies. So we apply again here to the constant time gap policy we just talked about in the last slide. And then we see we can derive the string stability conditions for constant time gap based adaptive cruise control system. These conditions are inequality conditions that relate to the three design parameters, which are the two feedback gains. So the Kv, the feedback gain on speed error, and the Ks, the feedback gain on gap error, and the Td is the desired time gap. So these are the three design parameters you can manipulate or tune, and to the system delays, which CACC and tau. Okay. So and with these inequalities, we can actually visualize the influence of these design parameters and the system delays to the string stability property of the platoon. Let's have a look at the influence of delay and actuator lag. So here is again, I repeat the magnitude of the disturbance transfer function. The three figures are the magnitude plot at three frequencies of the disturbance. The horizontal line axis is always the sensor delay, and the vertical axis is the actuator lag. And the values in the contour plot are the magnitude of the disturbance transfer function, let's say. When it's larger than 1, the string is unstable, otherwise string is stable. You can see that in all at different frequencies, increasing the sensor delay always result in a higher magnitude of the disturbance transfer function. So that means the increasing sensor delay always has a negative impact on string stability. At low frequencies, let's say this 0.1 release per second, increasing this actuator lag also leads to increase in the magnitude of disturbance transfer function. So that means at this frequency, increasing actuator lag also destabilizes the string. However, when we look at the high frequency, increasing the actuator time lag actually results in lower magnitude of the disturbance transfer function. So it tends actually to stabilize the string. And this actually can be clearly seen in this equation. You can see this, the square of tau is always positive, and at high frequencies, this higher order term of omega dominates this magnitude transfer function. So you would tend to get a stable string at high frequencies when you have actuator lag considered. Now, when you assume zero actuator lag, you can actually, I didn't show the plot here, you can actually get string instability at high frequencies, which is of short wavelength type. But in reality, the empirical evidence of real-world traffic disturbances only support low frequency type. So this has been well documented in Dr. Trevor's work. And so do the string stability conditions with actuator lag. So if you look at these conditions at high frequencies, there won't be disturbance, or there won't be string instabilities. Okay, so that means we have to be careful when you model a sensor delay or reaction time without considering the actuator lag. You may get into a string instability of high frequency disturbance, but this is not realistic. So this is one message I want to say. Now let's look at the influence of the three design parameters we mentioned: the time gap, the feedback on gap error, and feedback on speed error. So in these plots, on the top three plots, we see the different region of in the Ks and Kv plane under a certain time gap setting. And this green and the blue region are stable region, and the orange and dark red region are unstable region. And the top three figures are results with delay considered. Okay, and the bottom three figures are the same parameter setting but without any delay. So what you see clearly is that when we don't consider sensor delay and actuator lag, you really overestimate the stable region. Okay. Now the consequence is that you may get you overestimate the benefits of such systems when you use these to simulate ACC or CACC, and this may even lead to invalid parameter settings that you assume to be stable, but in reality, actually, they are not. Okay. So here is another message that I want to bring across. So we really have to be careful to derive conclusions when you parameterize your controller or your model based on a zero delay assumption. Now, as I said, I am an engineer. I also want to solve problems. So we know that delays are detrimental for string stability, and we want to see how we can compensate for delay. Now there are intuitive solutions is that we at the current time t we don't have the current state information. We only have delayed state information. So one of the solutions is use a state predictor, and one of the well-known is the Smith predictor, and then use the predicted state still in the state feedback controller. I listed two examples here, and there are other examples of this in this line. I want to talk about the other four solutions, which we have done some work. This including using model predictive control to compensate delay, formulating a new desired spacing policy that we anticipate the delay already in the spacing policy, and reformulating the CACC from time domain to space domain, and resulting to vehicle to infrastructure communications. So let me get you through these four solutions I listed here one by one. So let's start with the model predictive MPC based strategy. I list here a minimal formulation of MPC. So there is no need to understand all the notations I listed here. But for MPC, you do need a cost function or cost functional you want to minimize. And you need a model for your system dynamics. And you need an initial condition at current time t0. And these state variable x and control variable u are often subject to some constraints. Now, the idea of MPC is that at the current time t0, you want to use the initial condition and the system dynamics and some arbitrary control input to predict the system trajectory in the future, which is the solid red line. And you want to optimize this trajectory of u such that the difference between the predicted trajectory and the desired trajectory is minimal to some extent. And then for an MPC setting, I don't use all the predicted optimal control trajectory, but only use the first sample, okay, to regulate the system. And then at next time step T1, when we have new sensory information or communication information, I redo this optimization again, and again I only use the first sample. So this is a general idea. Now, when we have delay, there is a problem, right? So the problem is that we don't have the current state information, and we only have a delayed information. How can we do the MPC in this setting? So I use the figure here to illustrate the problem and the possible solutions. Now at this time t, we want to have this state information, but with the time delay, we don't. We only have this state information at previous time t0 minus CACC, okay? And then how do we do the MPC? We still need to have this state information at t0 and make prediction. A naive strategy, which I called, is to simply use this state information, add the information at the time t0. Okay, this is visually shown here. So you basically drag the state information to the current time, and you can clearly see there is an error here. This is on the top is the real state you want to use, but actually you don't get the information, so you use this old information. The second option, because we are doing MPC, so it's to shift this prediction initial time from t0 to t0 minus CACC. And then because typically the TP will cover a longer time than this t0 plus t1, so I can still use this initial condition, this initial time, to compute some optimal control trajectory that span over this t0 to t1, and I use this sample to implement to the real system. Now the problem is here that you already applied the control, right? So in this interval, and you know actually what you applied. But if you shift your starting time from t0 to t0 minus CACC, you still need to recompute an optimal control input in this interval. And this may be different from what you have applied, and there is a potential error there. So that's the drawback for the second option. The third option I'm proposing here is, we have this delayed information here, and we have a system dynamic model, and we have applied the control history at this interval. Okay, and we use that to estimate this value, the state at this t0. And mathematically, this is just an integral. So what I want to estimate is the t0. I integrate using the initial condition So here I use a different notation for delay, but you know what I mean here is this state information. And I know the control history in this interval. Okay. And then I can get an estimate of this state here, and then I start with the MPC again. So that's the idea with the MPC-based strategy. And with that, I can show this simulation that so this is the case without any delay compensation. This is the option 3 I used with this MPC-based delay compensation strategy. You can clearly see the benefits. Now, this is the first solution. The second solution is the new spacing policy. And in this setting, I show a platooning system where each follower in the platoon receive information not only from the leader, not only from the direct predecessor, but also from the leader, because 0 in the platoon. What you see is the plot to show the influence of delay is that the left 3 trajectories are those without delay of 21 vehicles. So you see the disturbance attenuate. So the string is stable, but with only 0.02 sensor delay and the 0.1 communication delay, the string becomes unstable. So we want to reformulate a gap policy such that the platooning system becomes stable again. And to do that, we again need to reintroduce some basic formulation. Again, we use the same vehicle dynamics I introduced before. So the position, speed, acceleration, derivatives result in this actuator time lag. And there are 2 spacing errors we need to compute. One is to the direct predecessor, and this is the desired gap, which is constant in our setting. We use a constant spacing policy here, and so then you basically compute the difference between the 2 positions of ego vehicle and the predecessor, and the desired the constant spacing. We also need to compute the spacing error to the platoon leader. And using the same notation, you can see it formulated in this way, the position difference and the sum of all the desired spacing of all the vehicles in between them. The control law is formulated to eliminate the 2 spacing errors to 0. So I have to, you don't really have to know all the notations here. So let me show you what are in this control law. So the first one is the acceleration of the predecessor. So this is a feed-forward information. Basically, you want to copy what your predecessor does. The second one is the leader acceleration. Is also feed-forward information. So you also want to try to mimic what the leader of the platoon does. The third and fourth term are the spacing error and its derivative with respect to the predecessor. We want to eliminate them. And the last 2 terms are the spacing error and its derivative with respect to the platoon leader. So this is the idea for the control law. It's the state feedback for feed-forward control law. Assumptions made in this work is that there are communication delays in whatever communication link we assumed. So the position speed of the predecessor we assumed is obtained from onboard sensors, so is subject to constant delay, delta S. Acceleration of the predecessor we assume is obtained from vehicle-to-vehicle communication. We has a bounded delay, sigma p, and the position speed acceleration of the platoon leader is obtained from vehicle-to-vehicle communication and is subject to bounded delay. We have an upper bound and lower bound of the delays. We also assume that this the consecutive so the leader information delay between 2 consecutive followers are also bounded. So So the communication delays are time varying, so they can be time varying, but we know their upper and lower bounds. And the vehicles in the platoon can have different delays and different desired gaps. So these are the assumptions we made when we designed the system. So let me give you some insights into the two error terms when we have delays. So when we have delays, something interesting will show up here. So when we have delay, we don't have the current, we only have a delayed information of the leader speed. And we can actually reformulate this desired gap policy by moving the delay term to the right-hand side. And you have to believe me that I did the calculus right, that when we have synchronized the signal to the same time t at the left-hand side, we add an integral in the delayed time window for the leader speed. So basically, this is the distance the leader traveled in the delayed time window. For the predecessor gap error, we can do the same. So we move the delay of the predecessor to the right-hand side, so that we only compare the gap error at the same time t, and then you can actually sum all the predecessor gap errors, and you also get this same term of this difference between the platoon leader position and the eagle vehicle position. And here the extra term is the basically all the distance traveled by all the vehicles in their respectively delayed time window. The insight here is that when there's no communication delay, these two terms vanish, and then the two gap error terms basically have the same goal, because you see that these desired spacing are the same. But when you have delays, communication delays, heterogeneous delays, these two terms are different, so resulting in conflicting error terms. Your controller are tracking two different terms that cannot be resolved. So that's leads to the instability that we see in the simulation. What we propose is to add an extra term. This term is actually represent I use GI here to represent a memory time window. So this basically says, apart from the constant spacing, we also add a distance that the predecessor I-1 traveled during this memory time window. And how to select this memory time window is that it should be larger than the maximum delays of these different delay sources, from sensor delay, communication delay, and the delay difference between the consecutive vehicles in the platoon. With this new policy, we can recompute the predecessor gap error and leader gap error. So the GI will appear in this position of the predecessor, and HI will appear in the position of the leader gap error, leader position term. HI is not a new parameter, but a sum of the GI of the memory time window for each vehicle between the subject vehicle and the leader. Okay. So with this new error term, we put again them back into the control law. What you see here is that so it's the same control law with the same control parameters, but only the time argument of the signals are different. So what I want to highlight here is that all the signals related to the preceding vehicle n-1 now becomes t minus GI, and all the signals related to the platoon leader signal is the time argument is t minus HI. So both for the acceleration, speed, and positions. So at least for each vehicle, the signals are synchronized. And if you plot this magnitude plot, you can see that this is without treating the delay, this platoon example is unstable because the magnitude is larger than 1. But with our new formulation of the spacing policy, we get a stable string. And this is clear also from the simulation results. On the left is the nominal system without any delay is stable, but with communication delay, the string becomes unstable. And with our new spacing formulation, even with delay, we can compensate that such that the string becomes stable again. Now, this idea of reformulating spacing policy appears to be generic in the sense that it can be applied to constant time gap policy of CACC with both communication and actuator delays. So I will stop the second solution here, but go quickly to the third solution, which is to reformulate the CACC system in the space domain. So the idea is that using distance traveled as independent variable and the time as dependent variable. The advantage is that when you look at a certain position, so you want to regulate the ego vehicle such that it keep a desired gap to the predecessor with at the same position, and then often at the time t1, you already know the history information of the predecessor. Although there is a delay, so as long as the desired time gap is larger than the delay, you actually can have this information. Now, this is the idea. How to do that? We need to do some translation from time domain to space domain. I guess I need to hurry a bit here. So the time independent variable is changed from time to space, and the dependent variable is swept. And in the time domain, you have the first derivative of speed, and then second one, acceleration, third derivative of jerk. And in this space domain, we use similar concept to call it the slowness, moderation, and jerk. And then the relatively dependent variable in the time domain is the distance highway, but in space domain, we call it is the time gap. Now, in the state space formulation is we formulate the state as the difference between the desired time gap and the real time gap, and the difference between the slowness of the ego vehicle and the predecessor, and the moderation. And this is equivalent to the spacing error, speed error, and acceleration in the time domain formulation. And the control input here is the desired moderation. This is equivalent to desired acceleration. And for the objective function, we just use a quadratic form. Here is the simulation result. In theory, we can prove that this is string stable. And here I show the simulation that if you see this baseline time domain CACC, the dashed line is the follower profile, and the disturbance is larger than the predecessor, which is the red line. In the space domain formulation, and if you zoom in, you can see that the disturbance is smaller than the predecessor. Okay, so this is the third solution I want to mention. The last one is to resort to vehicle to infrastructure communication because their V2V is nice, but there are uncertain business models, and you need a decent market penetration rate to get platoons. What can we do at low market penetration rates? So here's an idea that we thought that can be useful to stabilize a mixed traffic string. Now, suppose the intelligent infrastructure can obtain the position speed information of a string of vehicles and estimate their parameters. And one of the vehicles is CAV can communicate with the intelligent infrastructure about its exact control and system delay parameters. So with that, you can actually compute the string stability condition of the platoon. If it is unstable, you can adapt these CUV parameters, the desired time gap, the feedback gain on speed error and gap error, to develop the platoon. And after the disturbance, the CUV can restore to its default parameters. Here's a simulation with perfect model. So the fifth vehicle is when we don't do any adaptation, disturbance is larger than the first vehicle. But when we do this adaptive driving parameterization, you see the disturbance is damped out. Now we also simulate the different positions of the CAV with the imperfect model. So there's a mismatch between the model estimation and the simulation. You can still see that at the different positions, the last vehicle, the disturbance is smaller than the first vehicle. This is the fourth vehicle is the CAV, and the third vehicle is the CAV. Let's come to the end of the talk. There are assumptions that we use in model and the design of the ACC and CACC. We really should be careful instead in order not to overestimate the benefits and in order to avoid invalid modeling and design results. The delays are intrinsic properties and have detrimental effects on string stability, and the influence of parameters on string stability can become non-monotonic under delays, so we really have to be careful there. I illustrate a few strategies that we can use to compensate for delays. Thank you very much.
Thank you, Dr. Wang.
Yeah, the first that if you are interested, yeah, I will stop the talk here and open for questions.
Okay, great. Yeah. Audience, please feel free to unmute yourself to ask questions, or you can type them in the chat box. Thank you. We're really seeing a lot of great contents here. I have a question first. So can you go back to the solution 3? You went a bit faster there.
Yeah.
The space domain formulation. You mentioned you use your leader's trajectory as a reference. Can you elaborate a little bit more on how you use it as a reference? Is it in similar to MPC or something else?
So this is indeed an optimal control MPC type formulation. So at each space position, I want to regulate the ego vehicle such that it keep a desired time difference to the predecessor. Now, when you are at this time, this position is history information of the predecessor. So although there is delay, but you mostly know this position. That's why this formulation is robust to communication delay.
Okay, I see. It's actually similar to the well-known Newell's model, but now your x-axis is space.
Yeah,
the y-axis kind of reverse the space-time diagram. Yeah, so you try to I got your idea. Yeah, very very neat idea. Thank you. Yeah. Oh, speaking of the arrow, what did you measure? Is it how do you define the arrow term here?
So in this space domain formulation, you mean?
Yeah. When you compute the cost,
so
it's based on time.
So the difference between the desired time gap and the real time gap. And the second one is the difference between the reciprocal of the speed, and third one they relate to the acceleration. So these three terms equivalent to in the time domain, the spacing error, relative speed, and accelerations.
Okay. Have you already published this work, or is there a paper so I can check them out later?
This is the paper is here.
Okay. I see. Excellent. Thank you. Okay, I saw an audience have some questions here. Suyuan, please go ahead.
Thank you, Dr. Wang. And my question is mainly about maybe some extension because the research you show us is mainly about in my opinion, is some kind of deterministic time delay. I mean, it will change, but it will change for each vehicle. It's a unit, right? And actually, in real world, sometimes the delay is time dependent. It will, the sensor delay is sometimes it's larger, sometimes smaller, and maybe in your opinion, how to deal with this question, or maybe how to use some method to solve that. Thank you.
Yeah, I think so. This I want to emphasize a bit the second solution approach, the new formulation of the spacing policy. Here already for the communication delay, we do not assume constant. Okay. But we assume there is a time step for every signal, so you know the time step of each signal. Here in this formulation we assume the sensor delay is constant, but this can be relaxed in this solution direction. So we have a current work that we do not assume the sensor delay is constant, so it can still work in this solution. For other solutions, I think if the variation are still acceptable, let's say we roughly know the lower and upper bound of the variation, so the several solution direction can still work. Okay.
Got it.
And if the variation is unbounded, I don't know how to deal with it.
Got it.
Okay, thank you, please.
Okay, hello, Mom. Thank you very much for presenting your work at our webinar. It's really interesting, so I really love it. Thank you. I have 2 questions. One is, that's perfect slide. So in this case, I think I may miss something. So if I am interested in the head-to-tail string stability, so of course, I need the information of the first leader, like the vehicle 0 here. But why do I need the information of those in between?
Oh, yeah. So those in between are mainly the acceleration of the predecessor. So this information, so you can say you get the predecessor speed by by onboard radar with your ego vehicle speed, and then you differentiate the speed to get the acceleration of the predecessor. But this signal is very noisy, so actually you don't use that in your ACC control or CACC control law, but use the communication. So when the predecessor communicate, the acceleration is much more accurate and can be used in the control law. That's in this setting why we use the communication with the predecessor.
No, I think maybe I did not make my question clear. I was wondering that if I am vehicle 2, let's say, and then I only care about the stability from vehicle 0 to me, so I would imagine that I don't need the information of vehicle 1. Do I need that?
Yeah, okay. So with this information, which is appear to be feed forward in your control law,
I think that's the term, because you want to mimic the
advantage in stabilize the string.
Oh, I see. Interesting. Thank you. Another question is, in your last solution, we used the V2I. So do you think there will be an advantage in terms of the communication delay and error? Because I imagine that it will take longer time for the infrastructure to do the computation and then pass the message back.
Yeah, I think that's a good point. I did not consider these delay.
This one.
Yeah, what I want to say is that here I consider a traffic disturbance, which, let's say, typically has a duration of 10 to 20 seconds, and then in this setting, you would say that a delay of 0.5 seconds doesn't really effect. And you can also argue that because in the intelligent infrastructure you can have a bit more computation and communication power, such that you can have more investment in the infrastructure, so that the communication system is more reliable and more is much better than the onboard communication system. So, but I simply in this work I did not consider that, and that's indeed an assumption.
Yeah, but this framework, I think it can be directly applied to, for example, those autonomous vehicles that have very strong sensing capability that can just directly sense, right, the vehicle nearby. So, yeah.
Yeah. So let's say if you have a sensor that you can sense not only the direct leader and follower, but also a few vehicles ahead and behind, then this concept can be used without this vehicle-to-eye communication.
Yes. I think we do see that for example from like Waymo's self-driving cars, they are able to sense up to 5 or even 10 vehicles ahead and option. So I think they can do this directly.
Yeah, I think for those expensive luxury autonomous automated vehicles, they do have the potential, but I'm not sure that's scalable to production vehicles, because those sensor sets are quite expensive.
Yeah, that's true. For future work. Well, thank you very much for the presentation. I think we have some other questions there. Oh no.
Actually, I want to follow up the questions here. Okay. I think Zhou-Yang, you can go first.
Hi, Meng. Thanks for the gorgeous presentation. So I also have some questions on the infrastructure assisted approach. So in this case, do you think that the conventional vehicles are time invariant, which means that the behaviors will not change over time? So if that's the case, do you also justify using like the field test data during like different traffic oscillations, the parameters is almost the same?
No, that's we made quite some strong assumption here, as I said up in front, which is not really realistic. We assume the intelligent infrastructure can measure the position speed more or less accurately, and use that to inverse some car volume model parameters. Okay, and we didn't assume that the human drivers are time varying in their parameters. So that's the assumption we made for the time being. And I don't have empirical evidence, but this can be an interesting work to investigate it. To what extent, with a powerful roadside sensing system, that you can estimate the behavior parameters of human drivers.
Thanks so much. Yeah, that's all my question.
Okay. Dr. Wang, I have a follow-up question about the advanced sensing technologies. So recently, I got the chance to drive a Tesla vehicle. I noticed that on curves, especially on highways, Tesla on its autopilot display, we can clearly see Tesla is able to detect multiple leaders, sometimes 3 to 4, and at the maximum, Tesla claimed that they can detect even more than even a dozen of vehicles.
Yeah.
So my question is that I always fear the boundary between ACC and CACC is vague to me, and I like the definition at the very beginning. You said ACC, by your definition, is some system. It's based on its pure sensors, not communications. So with that being said, and some ACC vehicles can already detect multiple leaders. So what's the difference between ACC and the CACC systems? Does there still exist a difference if ACC can detect multiple downstream waves?
Yeah, I think the difference in terms of the controllers, if you can see multiple vehicles ahead, then from the controller formulation, an ACC can be then converted to a CACC. I think the difference is at the moment, at least, based on that using vehicle-to-vehicle communication. For instance, we use this term as the feed-forward term, and the quality of this signal is very important. As I said, that you can even use onboard radar to estimate the predecessor acceleration information. But this is, and then you can in the formulation formulate an CACC using onboard radar. But the signal is so noisy that you cannot use that in your controller design, in your control law. So that's why people then use vehicle-to-vehicle communication instead of only using onboard radar. I think the concept we are talking about at the moment are still whether you use communication or not. But the formulation-wise, an ACC can be using onboard sensors. You can, in theory, also formulate a CACC controller in that sense.
Okay. Yeah, that's a very good point. Thank you.
You're welcome.
Okay. Okay, I think we are already running out of time, and it's 11:07. And thank you everyone for coming, and thank you again, Dr. Wang, for the excellent speech. And we will upload the video to our YouTube channel very soon. And next week we will have Dr. Wenlong Jin from UC Irvine to give us another ACC webinar at the same time, 10 a.m. at US Eastern, and we look forward to seeing you again. Thank you. Bye-bye.
Thank you for the organization. Bye.
Thank you, Mom. Bye.
Thank you.
Benjue, can you hold on a minute? And Zimin, Zijian, if you're already here, okay, no, not anymore.